Presented by Caltech.
So it's my great pleasure tonight to introduce Rana Adhikari, who's an experimental physicist on our faculty in the Division of Physics, Math, and Astronomy. And he's focused his career on building the supremely sensitive LIGO interferometers that have generated so much recent excitement. So when Rana started his PhD at MIT, we now know the detection of gravitational waves was 18 years away. So it was interesting to me that Rana said that despite growing up near Cape Canaveral in Florida and watching all the shuttle launches and getting so excited about space, he decided not to pursue a career in space sciences because it was just too long a time scale. So it was interesting that he decided to work on LIGO, which was almost a half century from inception to this result. And he now tells me that he's looking to space as the next frontier for gravitational wave astrophysics. So I guess he's come full circle. Besides his childhood in Florida, another little-known fact that I just learned today is that Rana supported himself through school and graduate school by working as a car mechanic, which was very good training for being an experimental physicist, probably the best he received given he did go to MIT. I had to say that for the Caltech alums in the audience. But anyway, tonight Rana is going to tell you about the future of the amazing LIGO machine. Rana?
So I'm going to work a bunch of comparisons into my previous automotive life now that this has been revealed.
I want to know if you do quick and black.
Of course. Everyone in Cambridge does who works on cars. I didn't work on cars by choice in Cambridge, by the way. It was just I was unused to the effects snow has on cars from the south. I complained a lot when I was forced to work on these machines from Detroit when I was a younger teenager. It turned out to be very, very useful in the experimental physics lab because the kind of things that break down they look very similar. If you stuck your hand into a fan belt or a radiator or doing a head gasket in a gigantic Pontiac or something, it's not so scary to work on interferometers, just so you know. Well, so to give a little introduction to where this is, one of the things that excited me about getting into this field was that we would be able to do something which was akin to doing atomic physics and atomic spectroscopy on atoms, but to be able to do this on the most exotic things in the universe, neutron stars and black holes. And at the time when I started in the late 90s, the first detection of gravitational waves was just a few years away, and it seemed reasonable to get into the field. Whenever I give talks, I have trouble with lasers. I think this is, the universe feels something about me. I have a backup. So optical astronomy obviously started with the birth of human beings and eyes. It's been going on a long time and has been really advanced in the recent days. And the sky is now gives us a lot of information in different bands. There's the cosmic microwave background, infrared light, gamma rays. But at the time, the gravitational wave sky was empty. And I thought, this is a great opportunity. This would be like getting in on the ground floor of radio astronomy or X-ray astronomy. This is a great thing to do. So what are gravitational waves? This quote from John Wheeler, I think, gives us the best picture of it. Mass tells space-time how to curve, and space-time curvature tells mass how to move. Okay? And then there's this picture you can look at. Here's the sun, and the space-time is bent and here's the motion of the planet around the sun. But I like to give, okay, so here's an equation, but I promise you no more equations, just the first one. And I won't even write down everything here, but I think it's important to understand this one. On the left-hand side is the curvature of space-time in units of 1/meters squared. And on the right-hand side is this big conversion factor, and this T mu nu term here, which has to do with the energy density that you're using to make the space-time curvature. So this would be the energy density of the sun, for example. And what's this conversion factor? 10 to the minus 43, so 43, 43 points after the decimal point. And this, I think the way to, since Fiona mentioned cars, this is a little bit like it's just a conversion factor like miles per gallon. And so if you want to find out how many miles you can go, you take your miles per gallon number, which is hopefully bigger than this, and you multiply it by gallons. That's what you get. In terms of general relativity, what it means is that you're going to need a lot of stress energy if you want to make any curvature which is reasonable. And that's the reason why we here on the Earth, in our, although when I'm clenching my fist, there's some energy here, the curvature of space-time due to that is so minute that we usually don't have to worry about it. And then the exception, of course, is the system of GPS satellites where we take this into account. So gravitational waves, there's a lot of talk in the press about have they been, has Einstein been proved right or wrong? Is there evidence for it? Is this the first discovery? Well, here, it's funny, I looked this up, and when Russell Hulse was in Puerto Rico looking at the data from the Arecibo radio telescope there, I was, right at the time, I think to the week, when he realized that there was some funny perturbation to the pulsar he was observing, I was about 1 day old. So I'm not superstitious, I'm just telling you this is a coincidence. From this dot, I was intrigued. So he talked with his advisor, Joe Taylor, and they quickly realized that what they had was an actual pulsar in a binary system, and that it was a great laboratory for testing general relativity. And so they were able to time the pulses from this pulsar as it went around in a circle, and they saw over the years an analysis where Joe Weisberg was also involved, that the binary was slowly inspiraling as time went on. And here's the data just till 2005. They have data which goes much longer, but it perfectly follows the expectation from general relativity, and I think really proving that the energy lost from this binary inspiral was as predicted by general relativity and as predicted by the theory of gravitational waves. So this doesn't directly measure the actual stretching of space, but it tells you about, that energy is being lost, and it seems to be in agreement with gravity. So it's very good evidence for it. However, what they did not measure was this thing. And this is what we expect the effect of gravitational waves to be from a source like a binary pulsar. So imagine you have in space a bunch of rings like this, and each ring, let's say, instead of actually being a hula hoop, it's just a ring of beads. And so they're free to stretch. As the wave comes through, the effect should be that the circle stretches and expands according to the frequency of the gravitational wave. If you look carefully, you'll see also a few things. The stretching is always in the same direction, sort of along this axis, and it's contracting in this axis. There could also be a wave which is polarized in the 45 degrees direction to this, like you can have vertically and horizontally polarized gravitational waves. And another number to think about when you look at this is how much the stretching actually is. So in this case, when the ring is at rest, let's say it's about this big, and when it's fully stretched, it's maybe 2 times bigger than the resting position. So in this case, what we would say is that the change in length or the change in diameter of the ring or the hula hoop in one direction, it's about a factor of 2. And so in the jargon I'm going to use throughout the rest of this, we would say that the strain due to gravitational waves is approximately 1. Okay. So that's foreshadowing. So starting in the, I would say soon after these were predicted by Einstein in 1916 and 1918, there was a period of, let's do that. I don't have a plot, so I'll do this with my hands. This is something like theoretical uncertainty in the reality of the gravitational waves. And if you imagine time on this axis, whether they're real or not sort of oscillated like this in the belief of physicists. And this went on and on until a thought experiment by Richard Feynman in 1955. And he said, well, they could be real, they could be not real, but if you imagine their effect, and you imagine that movie we just saw, if those beads are immersed in some sort of medium, or if those beads are on a real hula hoop, the gravitational wave will come and actually move the beads around. And if there's some friction in the hoop, then some heat will be deposited in the hoop. And then once the wave is gone, if the thing is hotter, you can't really argue anymore about whether it was real or not. There's some real evidence. And so that argument and others mainly convinced people that this was real, it was the thing to do. But when people calculated how small they would be from any kind of known astrophysical object, like binary stars that we usually see, the number was so absurdly small that no one would touch it, really. It just seemed impossible, except for this man, Joe Weber. And he was an extremely bold physicist and engineer, and he had nearly invented the maser first and a few other things, maybe even radar. His ship was sunk while at Pearl Harbor. He survived. He was a very entrepreneurial. I mean, I can't even say that word for some reason. Entrepreneurial. He was a very bold man. And so he said, well, I'm sure I can do it. And so he built a system of these giant bars, and they would ring like a bell if a wave came through and tried to stretch it. And then he would put sensors around the middle of the bar and use these to read out a voltage. And he set these bars up on different parts of the country and looked for a coincident ringing of the two different bells. So throughout the 60s and up until the early 70s, he worked on this, and he started to see what looked like coincidences. Those results were not, we were not able to reproduce. I say we, but they were not able to reproduce those results. But one of his students, Robert Forward, came here to California to Hughes Research, and on his off days, he started working on this idea of building a laser interferometer, and he built it in a closet of his office or something. It was sort of a side project. Meanwhile, Ray Weiss at MIT started also thinking about what could be done, as he tells me, because he was forced to teach general relativity, and he didn't know enough relativity. So he thought this interferometer would be a trick to teach himself how to teach this course. So for different reasons, we have this invention. Kip Thorne started talking with Ray Weiss in the mid-70s, and then in 1980, Ron Drever, who had been working on this bar technology, moved to Caltech. And I would say these are really the founders of this idea of using lasers to detect gravitational waves. So here's a animation of how this is supposed to work. This cylinder is a laser beam, which goes to a 50-50 mirror. It goes into each arm. And then when the arms move back and forth, this wave, which is emanating from the laser, gets shifted by the motion of the mirror. The wave travels back, and when the two waves travel back, they interfere as they go to our photodetector here, which is a lot like a usual camera. When the waves are like this and they're out of phase, there's no light left here. When they're in phase, however, you get more light here, it gets brighter. And so the whole, well, to simplify it a lot, this is how the whole experiment works. And then, sort of like an inverse Matryoshka doll, we can slowly add on more complexity onto this thing and show you how it really works. But if you want to know how the measurement works, it's just by the interference of light from the two arms. So this is the theoretical timeline I alluded to before. And then there's this a bit of prehistory. The large-scale LIGO detectors at the kilometer scale started to be built in the late 90s. After I came to Caltech, we pushed through an upgrade of the first generation detectors, which we called enhanced LIGO. We're very creative with names. And then that was a sort of precursor and testing of a lot of the ideas which went into what we have today, which we call advanced LIGO. We've run out of acronyms here, so that's maybe the last. We first turned it on in May of 2014, and due to the work of really like phenomenally smart grad students that we happened to get in these years, we were able to go from first, switching on to first data taking in less than a year and a half, which is amazing. And then there's this event, which I'll talk about a bit later, which came in September. So I travel often to these different sites, and I can tell you, although Google says that there's this flight, there's no such thing. There's no way. If you try to get from here to here, it's something like a 20-hour up and down flight. But this gives you some sort of notion of the distance between those. It's something like an 8-hour flight, if you could make it. And why do I show you this? It has something to do with how the detection actually works. So one site is here in eastern Washington, and one is in northeast Louisiana. And it's 3,000 kilometers between the two detectors. And that's about the size of the moon. So the moon is roughly the size of the United States. And the distance from the Earth to the moon is about 100 times the size of the moon, or 100 times the size of the United States. So 8 hours across the country, and 800 hours if you flew to the moon on a 747, let's say. So that's a pretty long flight. But still, for light travel, that's only 1 millisecond one way, so 2 milliseconds to get back. The solar system, on the other hand, is 1,000th of a light year, or I guess 8 light hours. So it's quite a bit further than the moon, and I don't even want to imagine the plane flight. So astronomers like to use this unit of parsecs, which I'll use, but to think about it in terms of the solar system and the size of the moon, approximately 3.3 light years is a parsec. So when I say 100 kiloparsecs or something, that's around 300,000 light years. So here we are. This is roughly the size of the galaxy. The distance to the center is approximately 20 kiloparsecs. And that's more foreshadowing. So I'll tell you a bit more about what we've seen and how far away it was, but it's good to keep in mind the size of the moon and the galaxy and so on. So this is, I'm slowly going to add detail to how the experiment works, because I don't want to assault you with a bunch of busy diagrams right away. So you saw this easy idea before. There's a laser, a beam goes in, it goes down, up and down the arms of a Michelson interferometer, which are 4 kilometers long, and then they interfere. So this is all still going on. But here I've added the fact that we add some optics here at the beginning of the arms. And the purpose of these mirrors is, one way to think about it, is that the light goes in and bounces around about 300 times in each arm. And so effectively, it's as if we've extended the length of the arms by a factor of 300. And why would we do that? Well, it's because of the hula hoop movie that you saw at the beginning. The longer that our system is, the bigger that the length change is. If the strain comes in and you have a strain of 1, it means that your 4-kilometer arm will get stretched to 8 kilometers. So that's a good, healthy signal, and the bigger your detector, the bigger your stretch. So we want to make the signal as big as possible. I sigh because I'm about to enter into this endless topic of noise, which is my bane, but it's my life. So I sigh. It's like meeting an old friend again. So into this diagram, I've added some notes about what stops us from detecting the gravitational waves. if all that there was signal, there wouldn't be any worry. We would detect everything in the universe all the time. However, there's some things which block us. And it's basically the first ideas you have about what could be the problem. There's always problems with if the laser is too noisy, but let's say we've fixed that. The main problems we have to do with motion of the mirrors, or just a limit to how good we can make displacement measurements using a laser beam. So first of all, the ground moves a lot. Every earthquake bigger than magnitude 6 in the world shakes our detectors so much that we're unable to operate. And when this happens to you, you find out that the USGS has a text alert service. So your cell phone, you can make your cell phone buzz every time there's an earthquake that large. And then you get a real feeling for how often this happens. It happens all the time. There's earthquakes going on. So this is a problem to be solved. But we know how to do it enough so that we have an uptime of more than 50% for sure. We then, even if you're able to isolate from earthquakes and people walking by and trucks and nearby storms and hurricanes in the Gulf of Mexico, you still have the problem that you can't shield from, which is the usual Newtonian gravity. If I stand near one of our interferometer mirrors and I sort of do some sort of motion like this, the fact that I'm shaking around is changing the gravitational pull on the mirror, and that disturbs things. So we have to shield the nearby environment and exclude any people from getting close, and any trees from shaking nearby, and any animals from coming nearby. That can be done. Then you have the problem that, well, the mirrors that you're bouncing light off of are filled with atoms. And atoms are always problematic. Atoms are vibrating when they're at room temperature. In fact, that's the definition of temperature, is that these atoms have some sort of energy. So we can get around that also. The mirrors are made so beautifully that all of the thermal energy, the vibration of the molecules, is all concentrated at a few specific frequencies. So if you ever, if you live close to Old Town Pasadena, you'll notice that there's a few church bells which go off Sunday morning. And those have what we call a quality factor of a few thousand, which means within a factor of 0.1% or so, most of the energy is focused right at the ringing frequency of the bell. That's pretty good, but not good enough. Our mirrors are so pure that when you start ringing them, they almost never ring down. The energy just stays in them, and that means that the thermal energy is focused at the main oscillation frequencies of the mirror so well that there's almost no thermal energy left at the frequencies at which we want to measure the gravitational waves. We're able to hide it sort of like, well, I would say like sweeping it under the rug, but it's not, that sounds too negative. We're cleverly sweeping it under the rug. Finally, we have a limit which comes from quantum mechanics, which I'll get into a little bit later, but roughly it has to do with the fact that the light field which comes out of our laser is quantized, and it's built up of individual photons. So these individual photons hit our detector, and the pitter-patter of, can I do this? Yeah, that's my simulation of photon noise. This kind of pitter-patter is a masking rumble and hiss, which we're trying to detect signals on. And so it's tough, but we have tricks. This is yet another timeline. This tells you a little bit about how long this has all taken. The first gravitational wave bar detector here, this red square, was built in the 60s, and the sensitivity in these units of strain was around 10 to the minus 15, which means the first Weber bar could have detected a change in the aluminum bar at a level of 1 part in 10 to the 14 or 15, which is pretty amazing. It's a huge bar. But the sensitivity to an astrophysical source like a binary star system is 10 to the minus 7 megaparsecs. So what does that mean? That means 0.1 parsecs. So if you recall the picture of the galaxy, that means that that binary system has to be pretty much right next door. So luckily, he didn't know at the time how weak the signals would be, or else maybe he wouldn't have got into this business. These first two interferometers were the one built by his student, Robert Forward, here at Hughes in Malibu. And then there was some few technical improvements, but nothing major until the mid-'80s. This is the sensitivity of the first prototype interferometers at Caltech. I got into this field a little bit before this colored bar here. And after working for about a year, I experienced my first crisis of belief that the system was going to get better. I thought, maybe I should change fields. This looks tough. Nothing's happened. It's been a year. Nothing's getting better. What should I do? However, around that time, the large kilometer-sized systems were built, and this improvement that you see here by about a factor of 20 or 30 just came from having large systems. So I worked and worked and worked. 2004 came. Our progress started to slow down again, and I thought, well, we haven't seen anything. It's been a few years. Maybe I'll change fields again. It seems it's a long, 2 years is a long time to wait for something like this. Little did I know we were going to get a lot better. So for some reason, I stuck around, luckily so. By this time, our sensitivity to these kinds of binary stars had increased to the level of some around 100 or 50 to 100 megaparsecs, which starts to be in the region of interest. It means that you're able to see out to sort of thousands of galaxies. And you might think there's a reasonable chance of making a real astrophysical detection at that time. So yeah, as I said, in 2014, we first turned on these detectors. Let me explain this plot a little bit. On the y-axis here is the strain quantity I keep talking about. And on the x-axis is the frequency. This frequency is just the stretching frequency or so. The human audio band goes from 20 to 20 kilohertz. My voice is mostly in this band here. So all of the noise and signal and something that we're going for are I think easily understandable because they're at human vibration frequencies. So this yellow curve is where we thought we ought to be able to get to. And when we first turned the system on, instead we saw this pink curve. And we were off by this factor of a few hundred in sensitivity from day one. And to all of us, I think that seemed extremely good, because the last time we had tried this in 2001, when we first turned the thing on, we were off by a factor of 1 million. So we thought, how clever are we that we're not off by a factor of 1 million from our calculations? All right. It's a kind of optimism. But let me just explain what this y-axis means. So this is the fractional length change. And so this means if you have a system which is a kilometer long, and you have a strain of 10 to the minus 21, that means that you're looking for a change in the distance between those 2 points of 10 to the minus 18 meters. And so for scale, the thickness of my hair is about 100 microns. The wavelength of this red light is a little bit smaller than a micron. The hydrogen atom is 10,000 times smaller than that. The nucleons inside the hydrogen atom are 100,000 times smaller than that. And the distance that we were trying to measure is then 1,000 times smaller than that. And so I think it sounds ridiculous too. I don't know how else to say it. It's such a small number. And you have to wonder if someone comes here next year and just makes some arbitrarily small numbers, 34 or 45 or something like that, you shouldn't, don't sit here for that, because that person is a crackpot. You cannot do 10 billion times better than this. This is already hard. So anyway, we turned it on. It was like this. We wanted to get better. And if you ask me later, I'll tell you about it. But we found a bunch of technical problems and things that cause disturbances within the system having to do with stray electric fields and magnetic fields and electronics noise and the scattering of light from our mirrors, which go out into the system and come back. And slowly we were able to trap each of these things one by one and remove them. And around September 14th, well, this is October, but if you look at this brownish curve here, we were about at this level, so a factor of several away from the ultimate limits, but about as good as we could have expected to get, given that we hadn't turned on all of the bells and whistles of our system. So doing pretty good, I thought. Just to zoom in to what was going on that fateful morning of September 14th. The two detectors, the one in Washington, the one in Louisiana, were about the same, roughly speaking. But if you look here, there are a bunch of lines and features in this noise spectrum, whereas if we were limited by fundamental things like quantum mechanics and the vibrations of the thermal vibrations of the mirror surface, it would be very clean. It would be like a more smooth noise. And these peaks have to do with a bunch of different things. C means calibration line, so we put in vibrations of the mirror on purpose in order to calibrate how much exactly our measurement channel is measuring. P has to do with the power lines. So the neighboring towns near our detectors have a lot of, they like to use electricity, they watch their television, they like to have power at night, and so we have a lot of radiation from them and also from our own facilities. W are some wire modes which have to do with mechanical resonances in our system and so on. But beyond these lines, you also hear you see some scruff here. There's some peaky things here, and in this red one, there's this awful band of stuff. What is that? So at the time, we were still shaking things down, and so we were slowly fixing some of these things. If you visit one of these places, things look like this. The LIGO collaboration has several hundred people, but any given night, late at night, there'll be one lonely graduate student fixing something that nobody understands, but that seemed very important to that person. And this is what it looks like a lot. This is a common scene. There's a picture of me from 2003, and the only difference is I'm on this side of the room. Almost nothing has changed. So let's see if this works. So this is the sound of the detector, hopefully. Let me lower the volume a bit. So what you're hearing there is one of these sharp lines. And these are the glass fibers which we use to hold up the mirrors of the interferometer. And the glass fibers are vibrating just due to the thermal energy of being at room temperature. And so they're vibrating. And it sort of sounded loud, right? But that's how sensitive the system is, that the thermal vibration of wires is so loud. So then I've done a bit of signal processing. I filter out those wires and all of the other lines. And this is what the detector sounds like. It's a rumble. And the rumble is mainly coming from this type of stuff here at low frequency. So did you hear that little thump? Let me let it happen again. I didn't hear. I'm going to turn it up a little. There, that was it. So that little thump is the first observation of gravitational waves. That little thump. So we took the data and we matched it. We matched our best calculations from general relativity to it. And let me play you the signal now without the noise. I think the noise is interesting, but that's just me. So I'm looping it here. We didn't really have this many signals, but you hear it. There's a little bit of a swoop at the beginning. It's very short, but then this thump, to me, is the most remarkable part. The thump. What's that? What is that thump? So here it is, the signal. Let's look at this one first. So this is it in time. When it comes into our band, it only lasts for maybe 100 milliseconds at most. And it sweeps up in frequency from this almost inaudible place, 40 and 50 hertz, up through 100 hertz and to close to 200 hertz. So the thump you're hearing at the end is this burst of waves right at the end. And I've always wanted to stretch out the signal. I've been incapable of doing it, but I think it's good as it is. The thump, it a little bit sounds like if you hit a car tire with a tire iron. It immediately damps down. It's not like a bell. It's not like a guitar. It's not like any of those things. It's immediately damped. And the reason for that is really, it's a kind of breathtaking thing. The black hole itself, after merger, is ringing. And the reason that the oscillation goes away so soon, the reason that it's damped so much, is that the full energy of this black hole system is radiating into space. And so the energy is completely sucked out into gravitational radiation, and that's why the oscillation dies away. So let me show you a couple of animations, and then we'll come back to this one. Oop. No. Let's try this. So here's what we think happened. There were two black holes orbiting each other, each one about 30 times as massive as the sun. And here, this is not an artist's conception. This is a real astronomical background, which is not related to the black holes, but on which we've projected a real calculation, the real numerical simulation of what we think the space-time was doing at that time. And so the black holes orbited, they formed a common horizon, and then finally settled down into one massive black hole, and you could see the shaking at the end. This is another one. Here, the color coding is telling you about the curvature of the space-time. So these are the two black holes. You can see right under them, space is intensely curved in the negative direction, which means things will get trapped in the black hole. The orbit is being traced out here. Here we are in the early part. Around here is where it enters the band of our detector. We get a few cycles before the merger. As it gets closer and closer, you should watch. Hopefully we'll stop the movie. An interesting thing happens here. The curvature goes in the other direction, right at the end. And this is a really phenomenal, stormy, twisting tornado of space-time. And then they merge, and they form a common black hole. And this is so fast, the movie has to be frozen. But that's a really interesting point where two black holes are separate, they're forming, and then a neck forms between them. And there's a sort of black neck which forms between two black holes. And then it settles down, it's one black hole, it's shaking. And then these waves are the waves going out to infinity. And when I started in this field, one of the options was to get into numerical simulations of black holes. And I also thought that seemed impossible. I said, that's never going to happen. I'm going to work on this detector. And that only happened for the first time here in 2005. We had a clever postdoc working on it. And now the simulations done by the group here in collaboration with their colleagues at Cornell and in Canada, they're so precise that we're able to do what you see here, which is we take the actual measured strain, and if you notice the units here, 10 to the minus 21. So at the peak, it's just as I described. We're getting the displacement between the two mirrors, 2.5 miles apart, is 4 times 10 to the minus 18 meters. That's the fluctuation. We're able to take our best fit to that data and subtract it out and see that all that's left afterwards is noise. And the reason for that is the super high fidelity of these simulations. It's an unbelievable thing, and it goes from far out when the black holes are far apart until where they merge and they ring down completely. And we think that the accuracy of these simulations is so good that, well, they're in the lead. We need to make our instruments better to prove their simulations wrong. And that's the nice situation I think we're in. Let me skip forward. So a bit more detail on that what's really going on. So this early part is the in-spiral. It's coming together. It merges. It's sort of forming a common thing. And how can you estimate what goes on? Well, you heard the thump. You know it's sort of a low frequency. And, well, the Schwarzschild radius, which tells you about the size of the event horizon, roughly is this, where this is the Newton gravitational constant, the mass of the black hole, and the speed of light. And for the final black hole, which we have, which is around 60 times the mass of the sun, it's 183 kilometers. And if you take a black hole of that size, and if you imagine you could poke it with your finger and dent it, the horizon would deform, and that perturbation would travel around the black hole horizon at the speed of light. So you can calculate how long that would take, and that would be the perimeter of the hole divided by the speed of light. And if you invert that, you get this frequency. And in fact, this is the frequency of the thud that you heard at the end. It's a couple hundred hertz. I just want to zoom in because I'm somehow, when I wrote my thesis, I did a search for black hole ringdowns. And since I didn't find any, I'm now endlessly fascinated with the fact that we have a real natural ringdown to stare at. So I keep showing people this plot. Here's again the merger. Here I've taken the data from the two detectors and shifted one of them so they're on top of each other. Because the signal came not from right above, it went through one detector before another one. And then you can see this yellow curve as the calculation, and it pretty much matches up with the data, and you can see there's a few cycles of ringing at the end. It's amazing. I have full faith in my theoretical colleagues, but I would have bet big money that the first detection would not have been predicted correctly. And it's amazing that with such detail it actually happens. Yeah, so as I said, the signal came through Louisiana first, and around 7 milliseconds later it got to Washington. We used that information plus details about the waveform and the fact that the detectors are sensitive to polarization to localize it in the sky. This is the whole sky, and we think it came from the southern sky close to one of the Magellanic clouds, but our uncertainty is pretty big, like so. Yeah, pretty big is an understatement, but I don't know what else to say. I'm just happy there's a signal. I can't say anything negative about this. But in order to do better, we need two things. We need more gravitational wave detectors, and we need help from our colleagues in astronomy who have real capability to do pointing using optical telescopes and radio telescopes and so on, which I'll get to. People often ask, well, you're talking about this one event, and you looked at 2 weeks of data. How many events do you have? Do you secretly have 1,000 of them, and you're going to just keep us in suspense and tell us a little bit at a time? Well, this signal that I just told you about was extremely strong, and so we were really glad to see such a strong signal. But the majority of signals, which are coming from a huge distance away, are sort of at the threshold of what we can detect. So for us to tease those out from the noise and say unequivocally that they're real takes us a really long time. And slowly we're getting better at doing it faster and faster. So I don't know if I can really, I assure you, I say this without any basis, I assure you that in the future these things will come out much faster and you'll know about them better. But even so, from this histogram, which shows something like our confidence in detection and the probability of false detections, you can see our estimate for the background, if there's no signals, is something like this. And there's a little bit of evidence of there being other signals above the background. And so I think you can do the arithmetic for yourself. This is 16 days and we have 4 months of data. Anyway, you see what that means. That's as much as I'm allowed to say. This is a sort of a baseball card description of the event that we had, of which I think this is a tremendous number here. The initial masses of the black holes were 36 and 29, and the final is 62, which leaves a big discrepancy. That means that just during the part of the signal that you heard, 3 solar masses of energy was converted into energy. Three solar masses converted into energy. By comparison, this is something like 10 to the 23 times more luminous than the sun during the peak time. And the luminosity of the whole universe is about 10 to the 48. So this single event outshone the entire universe by a large factor. And it's really strong. And I guess it's interesting. There are these events out there so bright, they're doing this kind of thing, and we've only just started to see them, which means there's a bonanza out there. If you want to find out more, we release a lot of the data publicly, and so you can download it for yourself and do what you like. I always wonder, I sort of flip-flop between different existential crises. And before this event, I said, oh no, what are we going to do? What if there's no signals? And we've just been lost for all this time. And then now I say, wow, there's a bonanza. There's so many signals out there. What are we going to do? It's the same kind of worry, but it just has the opposite sign. There's no happy medium. So what should we do next is a question. That's I have a lot of phone calls about this. Well, there's we as what should humanity do next? Well, there's a bonanza in all the different frequency bands. So roughly speaking, the frequency of the gravitational wave signal goes inversely with the mass. So 100 times heavier system, and the frequency will be 100 times lower, roughly speaking. Here we're way up at the high frequency end of the piano, and down here there's all this bass type of rumbling going on. This frequency scale is 18 orders of magnitude, so it covers a wide range of phenomenon. We think the supermassive black holes inside of galaxies are best seen by space interferometers and also by timing of all the pulsars when they're in a galaxy. These are both big efforts. This is ongoing and already has some interesting upper limits. Space interferometers we expect to be launched in the next couple of decades. The earliest gravitational waves, which basically span the whole sky, can best be detected by looking at electromagnetic radiation and more specifically the cosmic microwave background with experiments like Planck and BICEP. Less globally, I guess, what's next for LIGO? Well, there's all this bumpy noise that I showed you, which we're scratching our heads about and hope to fix in a few months. As soon as our detection was announced, we had a tweet from the Prime Minister of India who said, congratulations, and yes, I will put a LIGO detector in India also. So if I had known that, we would have worked harder and had a detection earlier. I've been going there since 2007 trying to convince people to put this in. So it was gratifying. Next year, we're going to put in the so-called squeeze light system, which I want to describe to you. And then in a few more years, hopefully improve mirrors once we learn how to do that. And then 10 years from now, I think we'll put in cold mirrors made of silicon, which has a bunch of benefits. But I think if you haven't heard about it before, this idea of squeezing light is really interesting. So if I'm not running out of time, I think I'll tell you about it. This is a kind of a fresh idea because I got very excited about this in May of last year. So if you bear with me, it's a little half-baked, but I like to talk about whatever I'm most excited about. So here you are, and this is just us, so I'll tell you. So this is our basic interferometer, as you've seen before. And this is a thing that I will describe to you, but usually there's no such thing, and the signal just comes out. And, well, that seems okay. But you can also say, well, the laser beam goes this way, it goes to these two mirrors, and then when it interferes here, it goes to this detector. And the question is, what's going back in? What comes out of the photodetector and goes back in? Well, nothing. Nothing's going back in. And what's the effect of putting all this nothing back into your system? Does the effect of nothing change the statistics of what you see? Does nothing somehow disturb the mirrors? And any, reasonable person would say, no, nothing doesn't do it. Nothing does nothing, right? But nothing does something, in fact. We know, as I said before, light is made out of discrete photons. They're hitting our detector, and that's the pitter-patter noise. We also know light has some pressure to it. You've heard of solar sails and so on, and there's those toy radiometers you can buy, which don't really show you the radiation pressure effect, but they talk about it. This is a cartoon from our friends at Berkeley, which I think nicely illustrate this. You shine light on a system. In this case, it's this ball with a spring, but for us, it's our mirrors hung by a wire. And the momentum from these individual photons hitting this thing shake the thing back and forth. And then here, when they try to detect it with their photodetector, this is a thought bubble of the detector. And the detector is saying, hey, I think this thing's moving. And it is, in fact. And it's because of the photon recoil. But why should this really happen? What's the thing that makes for discrete photons, and why is there a fluctuation in the photon number? Is that just how light is born and that has to be? Yeah, no, not really. When the laser light comes into the system, yeah, it may have some noise to it, but you stabilize it as well as you can. And since our system is so large and we have all of these mirrors, in fact, the light which is stored in our system has a storage time of about 1 second, which means that all of this sort of pitter-patter stuff, the story that I just gave you, all of that stuff gets averaged out by the fact that it's stored in our system for so long. And even if it wasn't, if there was some noise on this side, when the two fields interfere, they'd mostly be canceled out by the time they got here. So there's several effects which make it so that noise which comes in on the laser system actually doesn't bother you. In fact, what happens is the empty space which is entering our system from this unused port goes in and interferes with the field which is resonating in our system. And it has to do with the fact that, well, empty space isn't really empty. If you look at the fluctuations of the electromagnetic field in a piece of empty space, the field is constantly going up and down, and that's a limit due to quantum mechanics. And so when you look at this, the fact that there's nothing coming in from one direction, what's really going on is that there is emptiness going on, and the beating of the empty space, the fluctuations in empty space, with our ultra-pure, clean laser is what produces the fluctuations that we see. And the quantum fluctuations lead to momentum perturbations of our mirrors, which provide a quantum limit. And they also actually lead to the pitter-patter hiss of shot noise that you saw. So what can we do about this? Well, let me back up a bit. So the Heisenberg uncertainty principle, which tells us about the statistics of this noise of empty space, says the following, that you can't measure two related quantities with arbitrary precision. If you measure one of them extremely well, like for example, if you want to measure the position and the velocity of some particle, the better you try to measure the position of that particle, the more light that you shoot at it to do it, the more of this pounding from photons that you'll get, and the particle will be moved all over the place. And so you're trying to measure it better will impart a lot of momentum kick onto it. You won't know the momentum very well. For the electromagnetic field, which is the laser we're using to detect this system, there's a similar relationship which has to do with the energy in the electromagnetic field and the phase of the light. And as you recall from this diagram, we're counting on this phase of the light to be really steady for us to make absolutely very good measurements of the gravitational waves. So if we usually look at the signal that's coming out of our system, we see the following. There's a sine wave, and this sine wave is telling us about the sinusoidal motion of our system under the influence, let's say, of a gravitational wave. And there's this noise on top of it, which is this hiss, which comes from quantum mechanics. And what we know is that we can't violate this Heisenberg uncertainty principle. But what we also know is that there's some ways around it. So if all that you want to do is measure one thing, which is all that we want to do, we want to measure the phase shift on the light, you can say, well, let's just let the uncertainty in this variable become infinity. We don't really care what this one's doing. And so in fact, we can engineer the statistics of the light so that all of the fluctuation happens not here at the zero crossings of this sine wave where we would estimate the phase of the field, but happens instead at the peaks and the valleys where we don't have any information associated with gravitational waves. So we can do that, and that's the technique called squeeze light. And that can be done in a bunch of different ways, either using the tools of quantum optics, nonlinear optics, or some other ways. We've actually done it in the past, and we've done it on the tabletop. We did it here at the prototype 40-meter interferometer we have on campus. We recently did it at the 4-kilometer interferometer in Hanford. We saw the quantum noise reduced by around square root of 2. And we now have plans to build a system to give us a factor of 2 to 3 improvement using the squeeze light technique, and which should be installed in early 2017. But when we were thinking about this, we thought, well, this sounds good, a factor of 2, a factor of 3, but what's really the ultimate limits? How good could we do? Can we have a factor of 1 billion, or 1,000, or 10, or what's to be done there? And I think the way to think about it is that, so this is the part which is I'm not sure of. The way to think about it is that we're not limited by the quantum mechanics of the mirrors. We're limited by the quantum mechanics of space-time and the electromagnetic field. And the limit to what you can do with measurements of space-time using a quantum field is almost limitless. The limit to space-time is well beyond what we're doing. And as it turns out, because of this trick with the uncertainty principle, we can induce a lot more amplitude fluctuations than light. And so the limit for phase measurement, and thereby the limit for astrophysical gravitational wave measurement is nearly boundless if we can solve some technical problems with respect to the optics. This is not proven, but this is, I think this is a new revolution in our understanding of how quantum mechanics works with respect to gravitational wave detection. So look out in the next year or so for something like that. So just to finish up, when I first got started in the field, this was the state of astronomy. So you see the resolution in these things is a little bit worse. WMAP had not yet launched. We had COBE though, and if some gamma ray bursts and infrared and so on. Still, the gravitational wave sky was empty. There was these question marks. Is there something there? And I worked and worked and worked. Several years went by, and all of my friends from school had better pictures by that time. And this experiment, which I thought I was going to work on, I didn't. Worked wonderfully. Everything worked wonderfully, and still, there was this thing. And I told people soon there's going to be something there. And now, after 50 years, we have one dot. So there you go.